So you are talking about the drift issue. So I have already inserted this, but let us unlock this. So these two, I have selected these two locations for the shear wall. But remember that if you are selecting the location of the shear wall, it should not be parallel to each other. There must be a gap or two. For example, let us turn off this beam. You have to delete these, right? So you have to insert the shear wall in the location opposite to that one. So you can insert in here, you can select any other location. So let us select the location for the shear wall in here. This is actually for the purpose of understanding that how you control the drift issue in your structural system. So let us draw in here. So it is actually in one story. So undo this and click on the all story. And this is the corridor, and this is also another option you can use to specify the location for the shear wall. So there can be different combination for the shear wall. If it's still not controlling your drift issue, then the code gives you another direction. We will talk about that in a while. So let us go to the top and bottom plane and make it one story and delete these. Right. So now we are set to run the analysis.
Hello, sir.
Hello.
Yes, sir. Now I make okay my phone. Can you hear me clearly?
Yes, now your voice is clear.
Yes, sir. We did many shear walls, so I think can we make only one or two shear wall? How to afford economically? Because we did many shear wall. Is it enough? Only two walls. It's not enough.
It depends upon the geometry of your building. If it is controlling your demand with one wall or two wall, you can do that. But if it's not controlling, then you have to force the architect to give me more location to, so I can give the more shear walls in it, right?
So our building, I understand. Our building controlling the drifting more shear wall.
Yes, if you are you can afford more shear walls, so there will be less drift issues in your building.
Okay, I understand, sir.
Right.
Yes.
So there is another.
Sir,
Gigi,
okay.
yes.
Sir, our drift story is up to 7 story. So can we make our shear wall up to 7 story? Also, how to save the economy?
So you have to check the drift issue. For example, in our case, the maximum drift wall at the fourth or fifth story. So you can provide your shear wall up to fourth and fifth story, and you can ignore the remaining
Other
part
story.
of the the 12th or 14th story. You don't have to move your shear wall up to the top. But if there is no restriction from the architect, you can also do that.
Okay, sir. I understand. Okay. Thank you, sir. Sir, R8.5, I think it's from code.
R8.5 is the value that we've used in the definition of the earthquake. It is from the code.
Yes. Okay. Sir, in ETABS, we use only beam and column and shear wall to design, but slab and stair, what we will use that how to design?
You're talking about the thickness of the slab or wall?
No, reinforcement of the slab.
Your voice is disturbing. I didn't hear you clearly.
Sir, in ETABS, we use to design beam and column.
Yes.
Is that right? So what we will use to design it and slab and staircase? I think foundation we will use safe.
Right. You can design your slab and beams and everything in ETAB, but you can also cross-check it in SAF. If you are designing your system, frame systems, you have to design your frame system like beams and columns in ETABs, and you can design your slab and foundation in SAF.
In our project, sir, what we will use?
We will be using both. You will see, right?
Okay. Okay, sir.
So let us check for the Arctic X again, and for the storyline, let us keep that, and we will extract only those. So for the top, it is again, it is what that was 1.8, so now it is 1.4. So we will copy that. So now the drift issue is still not working for the lower stories. It is giving me more value at the second, and for the third, and for the fourth. So in this way, if there is, you will solve one issue for the one floor, and then there will be issue for the other floor. So for this, code recommends you to do the dynamic analysis of the structure. So if this issue is still not solving for the shear wall, so you have to go for the non-linear static analysis, that is time history analysis, right? So in our case, we do not have any restriction for the architect, so we can go further to give more shear walls, but you have to check for the location, in which location you have to give the shear walls. So you have to go for the deform shape, and then go for the Arctic X and click on apply, right? So now you can see that there is a significant deformation in here, right? So you can also show the animation. So you can provide another shear walls in this direction, but we are not further going into this, because you are familiar with the how to control the drift, in what direction you have to provide the shear wall. We'll move on towards our next section, that is the torsion irregularity. And then after the analysis, because it will take another time, because if I place another shear wall, if it will consume more time to run the analysis, then after that, if there is not solving any or issue, so again we have to give the shear wall, so it will take a lot of time, right? So you can do your practice. You have this model, you have these drawings. So if you have any issue, you can ask me. I will also show you the basic requirements for the drift issues, and there's an Excel sheet which finds you the location in which store there's a drift issue and how to resolve it, right? So the next one is our torsion irregularity check. That is the torsion irregularity in our building is defined by the Building Code of Pakistan in table 5.12, right? So torsion irregularity is defined, let me make it larger, that the torsion irregularity to be considered with diaphragm are not flexible. It means you have assigned rigid diaphragm to your slab. So the torsion irregularity shall be considered to exist when the maximum story drift computed accidental, including accidental torsion, at one end of the structure transfers to an axis more than 1.2 times the axis of the story drift of the two ends of the structure. So it means understanding the language of the code is a bit difficult. So I recommend you to please read it very carefully. So the conclusion of all of this statement is that you have this maximum displacement divided by the average displacement. So the ratio of these two should be less than 1.2, right? Should be equal to or less than 1.2. So this is the limitation, the torsion irregularity of the code. So let us open this Excel sheet for the torsion irregularity. So this is the Excel sheet for the torsion irregularity for the X direction. So how do we calculate this? So let us go to the ETAB and go to the display, show tables, go to the analysis, results, and then go to the displacements and click on the diaphragm, right? So diaphragm maximum average drift, click on this and click on OK. So a table will appear which will show you the maximum displacement, which is calling it as drift and average drift, and this is their ratio, right? So you have to select the story. So let us keep the story for the top. So let us go for the earthquake X123, right? And select the story. This is top.